All right, welcome back. And today we are going to do a problem called n queens. It's quite a popular problem because that's usually the problem that they use to teach backtracking. And yeah, indeed, today we're going to do backtracking. Okay, let's look at the problem. N queens is a problem where you find a way to put n queens on an n times n chessboard without them being able to attack each other. So, for example, if we do 5, then if this is a 5 by 5 chessboard, and then you're going to be able to put 5 queens in there without them attacking each other. Now, you can kind of just think logically. The max queen you can put is 5 because there are 5 rows, and there's no way you could put 2 queens in the same row because it means you could attack them, because queens can move diagonally and vertically and horizontally, so they can move like this. And then because of that, you know that 5 is, if it works with the 5 configuration, then that's definitely the answer. So that's like the first clue that later on we're going to think about in terms of optimizing. Now, if you think about the brute force way, then what you can do is you literally just backtrack. What you do is you go through all the single chessboard positions, you put a queen there, and then you continue putting a queen at a random place or the next place, and then you always check constantly if you can put it there or not, right? And then if you can't put it there, then you backtrack. You go back to the previous position and you try to put a queen somewhere else. And then slowly but surely you will get all of the queens, right? You get all of the positions, and then you just record the one that is the maximum. So that's usually how you do it in terms of brute force backtracking. But the thing about this question is we can actually do this a lot faster by being able to see if the queen is already on the row or the column or at the diagonal. So instead of looking at all the queens, because every time you put a new queen, you have to see if you are able to attack all of the other queens. And that's an O of N operation, because you have to look at all the other different queens and you do 4 different operations to see if they are attackable, right? So that's why we will show you later how you can do that. But first, just in case, I'm going to be talking more about backtracking because I feel like that's a fundamental skill or like tactic to use. And I'll just explain a little bit more, and then I feel like the more I explain it, the more people will get it. So I'll just explain this one more time. So let's look at the iPad. As you can see here, I kind of drew this already, but if it's a little bit confusing, I'll explain it. So here we're gonna have the beginning state, right? Begin. And then you can go, your decisions to put a queen can have four ways you can put a queen. So I use a 2 by 2 here because it's a lot faster to draw. If you do a 4 by 4, then you have so many decisions. You have 16 decisions right in the beginning, right? So in the beginning, you could put a queen on each one of these corners. Depends where you go. And then I'll tell you how backtracking works. So imagine if we just look at this case. If we look at this case, then you can put your queen in multiple positions, and that's exactly what I'll do. I'll try to put a queen here, and then I'll go to this state, right? So if there's a green queen, like a green Q, it means it's the new queen that I just put. So I could go on to this state, and I realize I can't do that because the queens can attack each other. So what do? I backtrack. And how do I backtrack? I take off that piece that I initially had, right? So then I backtrack, and then I go this side. Does this work? No, it doesn't. I backtrack, I go here. Does this work? Excellent. And then later on, I'll try to add more queens, but I'll realize it's impossible. No matter if I put a queen here or here, it's not gonna work. And then I record this as one of the states. So then once I do that, I actually backtrack all the way back here to begin, and then I will do that again. So that's pretty much what backtracking is. And in terms of implementation, usually when you look at backtracking, it's going to be pretty simple because essentially what you see is you're going to be seeing you do something and then you recurse on the function and then you take something out, right? For example, I place the queen on d5, okay? And then I recurse to see if it's possible, if I could find any state. And then after I finish recursing, I actually pop the d5 queen out of it. That's usually what backtracking does, is you put something, or like you change something, you recurse, and then you take off that change. And then that's essentially how you can do backtracking. It's always the same template. All right, so now that you understand how to do backtracking, I'm going to be talking about how to do this problem a lot more efficiently, right? So I drew something like this. It might not mean much to you, but I'll explain what this is. Okay, so here we have a 4x4 grid of the queens game. As you can see here, I have like a column. This is actually an array, and it says true, false, true, false. Can you try to guess what this means? So when it's false, it means there's a queen in there. It means I cannot put any queen further. And here is another false, right? False and false. So the only places my queen can be put is on these areas, right? According to the columns. So what if every time I put a queen here, then instead of having to look at all the other queens to kind of compare and see if you attack them, what you can do is you could just look at the column. If it's true, then I know I could put it in there, right? And then when I do put it in there, I'll turn this into false because I know that no other queen can be on this column. So the strategy here is to, whenever you put a queen, you want to update these arrays or these values so that in the future, when you add more queens, you can easily look up and see if you're allowed to put the queen there. Instead of comparing yourself to all the other queens to see if you attack them, you could just look at a column array and then maybe the diagonal arrays. So what about diagonals? How do we do that? How can we know if a queen is in the diagonal? Actually, let's talk about rows first. How do you know about rows? Well, rows is kind of easy actually, because the way we put our queens, we can just put one queen on the first row, then the second row, and then the third row. I'm not sure which column yet, I haven't decided, but you can just put queens in that order, because you know that once you put a queen in the first row, you're not going to be able to put the queen in the first row again. So you're going to be going to the second row anyways, right? So what about diagonals? What can you do? So I drew some numbers in this checkboard. Now, again, it might not mean much to you, but if you look at it, I realize that I can use the position of the square and use that to calculate which diagonal they're in. So there's two kind of diagonals. There's the ascending diagonal and the descending diagonal. Okay. So what are these numbers inside? The number inside is their coordinate. Like for example, 0, 0, the column is 0 and the row is 0. And then here is the one column and the row, right? So we have that. And then what I realize is that if I look at the diagonal here, if you add the column number and the row number, it's all 0, right? Because you only have this one. If we take this guy, for example, let's take this guy. This 3 plus 2 equals 5, and then 2 plus 3 is also equals 5, right? So, and then let's see this diagonal. In this diagonal, all of these numbers, when you add up the row and the column, it adds to 3. So as you can see, every diagonal, the sum of the coordinates of the row and column equals to 1 or 2 or 3 or 4, depending on how far you go. So what about the other diagonal, going downwards? How can we measure that? So what you can do is you do the opposite. You subtract, right? Here, what's 3 minus 0? Here, what's 2 minus 0? 2. What's 3 minus 1? 2. Here, what's 1 minus 0? 1. What's 2 minus 1? It's still 1. So as you can see, instead of adding them up, you could subtract them. And that is going to give you the diagonals here, right? This is -1, this is -2, this is -3. Cool. So what do you need? You're gonna need a few arrays. You got an array that keeps track of the columns, and then you need an array that keeps track of the ascending diagonals, and you need another array that keeps track of the descending diagonals. Cool. So what would be the algorithm? The algorithm basically would be for every row, you're gonna try to place a queen in depending on which column, right? And then you're gonna place the queen. You're gonna see if it's valid. How do you see if it's valid? You check the column array, you check the diagonal array ascending, and you check the diagonal array descending. And then if those are all good, then you put the queen there, and then you recurse, you call the helper function or you recurse on it so that you can add more queens. And then after you finish recursing, you take that queen off and you try to put it in another position. And then that's called backtracking. Cool. All right, let's code it up. All right, so first we're gonna call our function like n queens, and then we'll give it n, and then we will return a Boolean, you know, like true, for example. And then what we're gonna do first is we're gonna write the helper function. Let's just call it helper. And then for the helper function, this is gonna be the one that does most of the work. Remember when I said like you put a queen, you recurse on it, and then you take out the queen, and then you put the queen somewhere else? This is basically what it's gonna do. So I'm gonna need a lot of information. I'm gonna first of all need the array of the columns, the true, false, true, and stuff like that to see if I can put the queen in that column. I'm gonna need the ascending diagonal, and then also the descending diagonal. I made a mistake. It doesn't return Boolean. It returns like kind of like an array of positions, like 0, 1, like 0, 1, 0, 2, and stuff like that. Okay. So this is basically what we want to return. We want to return the position of the queens that is like maximum. All right. So now what we're gonna do is we're gonna start with the base case. So if the length of queen position is n, we know that once it reaches n, it's the max, because you cannot have more queens into our rows. Okay? All right. So now the current row would be how many queens we have already positioned, right? Because we do it row by row. And then what we want to do is we want to look through all the columns, and then see if we could place a queen. So when can we place a queen? If the column allows it, we're looking at our column array. If the ascending diagonal allows it, and if the descending diagonal allows it. And what I mean by that, it means no queens are in the way. Okay. So if this is true, it means there's no queen in the same column. And then for diagonal, remember what we said? We could add the row and the column to get that diagonal number. So if that is true, then that is good. And then descending, remember what we did? We took the row and we subtract that by the column, right? Because all of them have the same value if they're in the same descending column. All right. So if that's the case, then it's good. Then what we're gonna do is we're gonna place the queen. And when we place the queen, we're gonna turn the columns, ascending diagonals, and all that false. So we're gonna turn this guy false. We're gonna turn this guy false. And we're gonna turn this guy false. And then we're gonna add the queen position. We're gonna add the row and the column. And then what we wanna do, like I said, we wanna recurse, right? We're gonna recurse. So I'm just calling the same function, and I have the same arrays, the column arrays, the ascending diagonal arrays, and the descending diagonal arrays. And then next, what we're gonna do is we're gonna check if it's done. And then if it's done, then we return the position. Right, okay, so we recurse, and then now we backtrack. Backtracking means popping off what we already put there. By popping off, we have to reset these guys. Now they're back to true because we took out the queen. And then we're also gonna take off the queen here because we recorded the queen. And then at the end, after the for loop, I'm gonna return the position of the queens. And then in terms of the n queens, what we have to do is we have to set the arrays, the initial arrays. So in the beginning, there are no queens, so it's true everywhere. And then we call the function. All right, so now let's see if it works. Now let's see print n queens 5, for example. This should give us like all the positions. All right, cool. So here you can see it gives me a bunch of coordinates. Now, if we look at the, if we think about it, let's see if this is good. Okay, so imagine we have 5 of them. Let's see if these queens attack each other. So they shouldn't attack each other. So we have the 1, 0, 0. So we got a queen here, and then 1, 2. So row 1, and then 1, 2. Queen here, and then we got 2, 4, 1, 2, 3, 4, and then we have 3, 1, 1, and then we have 4, 3, 0, 1, 2, 3. All right, so do these queens attack each other? Diagonal? No, no, no. All right, that looks good. So yeah, so that's perfect. So that's pretty much n queens. And what is the time complexity of this? Well, like you said, you have one for loop that goes through the whole column, and then you do that for all the rows, and then yeah, so that means you do that n times, so that's n squared, because n is the size of the chessboard. So this is actually a lot better than what we had previously in terms of brute force, because then it would have been n cubed, because every time you put a queen, you're going to have to compare with all the other queens that have already been placed, which is another n. So it's going to be n times n times n, but now we're able to reduce that by using those arrays. Now, speaking of arrays, that's space complexity. So what is the space complexity? So you can actually just look at it in our code. Here, we added like an array of size n, an array of size n, an array of size n times 2, which is basically n, and an array of size n times 2, which is basically n. So in terms of complexity, the space complexity is O of n. All right, cool. So I hope you learned a lot. This is a very classic problem in backtracking. I'll see you next time.